IEEE Std 4.2013, Section 13.2 2.1 addresses the length tolerances for parallel conductors, particularly in high-voltage motor installations. This standard provides crucial guidance for ensuring proper electrical connections and performance in these systems. When dealing with parallel conductors connected to a 15 kV, 5000 horsepower motor using 500 kc mil conductors, it is essential to understand the allowable variations in conductor length to maintain balanced current distribution and prevent potential issues such as overheating or voltage imbalances. The standard specifies that for parallel conductors, a tolerance in length is permitted to accommodate practical installation considerations. Specifically, it states that the length of the parallel conductors beyond the first 15 meters, or 50 feet, can be reduced by 10 millimeters, or 0.4 inches, per meter, or foot, less than 15 meters, or 50 feet. This allowance recognizes that achieving perfectly equal lengths for all parallel conductors in a real-world installation can be challenging and that minor variations are acceptable within certain limits. The basis for this tolerance lies in the understanding of how current distributes among parallel conductors. Ideally, current should divide equally among conductors of identical length and impedance. However, even small differences in length or impedance can lead to unequal current sharing, potentially overloading some conductors while underutilizing others. By allowing a slight reduction in length for conductors shorter than 15 meters, or 50 feet, the standard helps to compensate for these variations and ensure a more balanced current distribution. To illustrate how this tolerance is applied, consider an example where the parallel conductors are only 10 meters, or approximately 32.8 feet long. In this case, the length is 5 meters, or approximately 17.2 feet, less than the 15 meter, or 50 feet, threshold. According to the standard, a reduction of 10 millimeters, or 0.4 inches per meter, or foot, less than 15 meters, or 50 feet, is permitted. Therefore, the allowable reduction in length would be 5 meters multiplied by 10 millimeters per meter, which equals 50 millimeters, or approximately 2 inches. This means that one or more of the parallel conductors can be up to 50 millimeters, or 2 inches, shorter than the longest conductor in the set, provided that all other installation requirements are met. It is crucial to note that this tolerance is not an invitation to arbitrarily shorten conductors. Rather, it is an allowance for minor adjustments to accommodate practical installation challenges. The goal should always be to maintain conductor lengths as close to equal as possible to ensure optimal current sharing. Furthermore, it is important to consider other factors that can affect current distribution, such as conductor spacing, termination methods, and the presence of any bends or kinks in the conductors. These factors can influence the impedance of each conductor and should be carefully controlled to minimize imbalances. In addition to the length tolerance specified in IEEE Std 4.2013, Section 13.2 2.1, other relevant standards and guidelines may provide further information on parallel conductor installations. For example, the National Electrical Code, or NEC, contains requirements for conductor sizing, insulation, and installation methods, which are essential for ensuring the safety and reliability of the electrical system. Consulting with qualified electrical engineers and adhering to industry best practices are also crucial steps in designing and installing parallel conductor systems for high-voltage motors. These professionals can provide valuable insights and guidance based on their experience and knowledge of applicable standards and regulations. In summary, understanding and applying the length tolerance for parallel conductors in high-voltage motor applications, as specified in IEEE Std 4.2013, Section 13.2 2.1, is essential for ensuring balanced current distribution, preventing overheating, and maintaining the overall reliability of the electrical system. By carefully considering conductor length, spacing, termination methods, and other relevant factors, and by consulting with qualified professionals, engineers and technicians can design and install parallel conductor systems that meet the highest standards of safety and performance. Moreover, when implementing parallel conductor systems, several key considerations must be taken into account to ensure optimal performance and safety. Firstly, conductor sizing is paramount. The ampacity of the parallel conductors must be sufficient to carry the full load current of the motor, accounting for any diverting factors due to ambient temperature or conductor bundling. NEC Table 310.15 details ampacity ratings for various conductor types and sizes under different conditions. Secondly, conductor material plays a crucial role. Copper and aluminum are the most common choices, each with its own advantages and disadvantages. Copper offers higher conductivity and corrosion resistance, but is generally more expensive than aluminum. Aluminum, on the other hand, is lighter and more cost-effective but requires careful termination to prevent oxidation and loosening of connections. Thirdly, insulation type is critical, especially in high-voltage applications. The insulation must be rated for the operating voltage and temperature of the system and must be resistant to environmental factors such as moisture, chemicals, and abrasion. Common insulation materials include cross-linked polyethylene or XLPE, ethylene propylene rubber or EPR, and polyvinyl chloride or PVC. Fourthly, termination methods are crucial for ensuring reliable connections and preventing overheating. Proper crimping or compression connectors must be used, and the connections must be tightened to the manufacturer's specified torque. Regular inspections and maintenance are also essential to identify and address any loose or corroded connections. Fifthly, conductor spacing and arrangement can significantly impact current distribution and impedance. Ideally, parallel conductors should be spaced as close together as possible to minimize inductive reactance. The conductors should also be arranged in a symmetrical configuration to ensure equal current sharing. Sixthly, grounding and bonding are essential for safety and to prevent electrical shock hazards. All metallic components of the system, including the motor frame, conduit, and enclosures, must be properly grounded and bonded to provide a low impedance path for fault currents. Seventhly, protection devices, such as fuses and circuit breakers, must be properly sized and coordinated to protect the conductors and equipment from overloads and short circuits. The protection devices must be selected based on the conductor ampacity and the motor's full load current. Eighthly, documentation and labeling are essential for facilitating maintenance and troubleshooting. All conductors, terminations, and equipment must be clearly labeled with their voltage, current rating, and function. Detailed wiring diagrams and schematics should also be readily available. Ninthly, regular inspections and testing are crucial for identifying and addressing any potential problems before they lead to equipment failure or safety hazards. Inspections should include visual checks for damaged or deteriorated conductors, loose connections, and signs of overheating. Testing should include insulation resistance tests, continuity tests, and voltage and current measurements. Tenthly, adherence to applicable codes and standards is paramount. IEEE standards and local regulations provide detailed requirements for the design, installation, and maintenance of electrical systems. Compliance with these codes and standards is essential for ensuring safety and reliability. By carefully considering these factors and adhering to industry best practices, engineers and technicians can design and install parallel conductor systems that provide reliable and efficient power to high-voltage motors. It is also crucial to remember that the specific requirements for parallel conductor installations may vary depending on the application and the local regulatory environment. Therefore, it is always recommended to consult with qualified electrical engineers and local authorities to ensure compliance with all applicable codes and standards. In addition to the technical aspects of parallel conductor installations, it is also important to consider the economic factors. The cost of materials, labor, and equipment can vary significantly depending on the size and complexity of the system. Therefore, it is essential to conduct a thorough cost-benefit analysis to determine the most cost-effective solution that meets the performance and safety requirements. Furthermore, the long-term operating costs of the system should also be considered. For example, using high-quality conductors and terminations can reduce maintenance costs and extend the lifespan of the system. Implementing energy-efficient motor control strategies can also reduce energy consumption and lower operating costs. In conclusion, parallel conductor installations for high-voltage motors require careful planning, design, and execution to ensure optimal performance, safety, and reliability. By understanding the technical aspects of conductor sizing, material selection, installation, termination methods, spacing, grounding, protection, documentation, testing, and adherence to codes and standards, and by considering the economic factors, engineers and technicians can design and install systems that meet the specific needs of the application and provide years of trouble-free operation. Remember to consult with qualified electrical engineers and local authorities to ensure compliance with all applicable codes and standards. Proper parallel conductor installation in high-voltage motor systems requires attention to detail in several key areas. Firstly, conductor identification is vital. Clearly marking each conductor with its phase and circuit designation is essential for safe and accurate maintenance and troubleshooting. Secondly, conduit selection is important. The conduit must be sized appropriately to accommodate the conductors and provide adequate protection from physical damage and environmental factors. Thirdly, pulling tension must be minimized during installation to avoid damaging the conductors. Using proper pulling techniques and lubrication can help to reduce tension. Fourthly, bending radius must be carefully controlled. Exceeding the minimum bending radius can damage the conductor insulation and reduce its ampacity. Fifthly, support spacing must be adequate to prevent excessive sagging and strain on the conductors. Using appropriate support hardware and spacing the supports according to the manufacturer's recommendations can help to ensure proper support. Sixthly, inspection and testing should be performed after installation to verify the integrity of the conductors and connections. This includes visual inspections, insulation resistance tests, and continuity tests. Seventhly, periodic maintenance is essential for maintaining the reliability of the system. This includes regular inspections, cleaning, and tightening of connections. Eighthly, record keeping is important for tracking maintenance activities and identifying potential problems. Maintaining detailed records of inspections, tests, and repairs can help to ensure the long-term reliability of the system. Ninthly, training is essential for ensuring that personnel are qualified to work on high-voltage electrical systems. Providing proper training on safety procedures, installation techniques, and maintenance practices can help to prevent accidents and ensure the safe and reliable operation of the system. Tenthly, emergency procedures should be in place to address potential hazards such as electrical shock, fires, and explosions. Having well-defined emergency procedures and ensuring that personnel are familiar with them can help to minimize the impact of these events. By paying attention to these details and following industry best practices, engineers and technicians can ensure the safe and reliable operation of parallel conductor systems for high-voltage motors. It is also crucial to stay up to date with the latest codes, standards, and technologies to ensure that the system is designed and installed to the highest standards. In addition, the selection of appropriate tools and equipment is crucial for ensuring a safe and efficient installation. Using properly insulated tools, personal protective equipment, or PPE, and testing equipment can help to prevent electrical shock and other hazards. Furthermore, using specialized tools for crimping, stripping, and terminating conductors can help to ensure reliable connections. Investing in high-quality tools and equipment can pay dividends in terms of improved safety, efficiency, and reliability. Moreover, it is important to consider the environmental impact of parallel conductor installations. Using environmentally friendly materials, minimizing waste, and implementing energy-efficient practices can help to reduce the environmental footprint of the system. For example, using recycled materials for conduit and enclosures can help to conserve resources. Implementing energy-efficient motor control strategies can help to reduce energy consumption and lower greenhouse gas emissions. In conclusion, parallel conductor installations for high-voltage motors require a holistic approach that considers technical, economic, safety, and environmental factors. By paying attention to detail, following industry best practices, and staying up to date with the latest codes, standards, and technologies, engineers and technicians can design and install systems that provide reliable, efficient, and sustainable power to high-voltage motors. Remember to consult with qualified electrical engineers and local authorities to ensure compliance with all applicable codes and standards.